Hello and welcome to this video on finding the inverse of a matrix. So finding the inverse of a matrix is a very important process, and we're going to use that a lot going forward in the next section of work. The inverse of a matrix is defined as being a matrix A inverse, which we write like this, such that if we take A, the original matrix, and we take the inverse matrix and multiply them together, we get the identity matrix. So I've got a matrix here, and I've already worked out its inverse. Let's see what happens if we multiply them together. So we're going to get 4 minus 3 is 1. We get minus 1 plus 1 is 0. We get 12, take away 12 is 0. Minus 3 plus 4 is 1. So that's what an inverse matrix does. If you multiply a matrix A by its inverse, then you get back to the identity matrix. If a matrix has a determinant of 0, it has no inverse and it's singular. And that is important to remember. If it has got an inverse, then it's non-singular. Also, we sometimes say that if a matrix inverse exists, then the matrix is invertible. So for finding a 2 by 2 matrix, this is very straightforward. We interchange the elements on the leading diagonal. So we swap these two numbers over. We change the signs of the other two elements. So this becomes minus. Both of these change sign. And then we divide by the determinant. For this example I chose here, the determinant was 1. So that didn't make any difference, but it often won't be 1. So the inverse of matrix M is given as 1 over the determinant multiplied by the matrix. So the determinant must not be 0. And if a matrix represents a transformation, then the inverse matrix reverses that. So when we come on to the chapter on transformations, if the matrix is a rotation of 90 degrees clockwise, then the inverse will be a rotation of 90 degrees anti-clockwise. Some transformations are self-inverse, and some matrices are self-inverse. The method for a 3 by 3 matrix is much longer and fiddly, really. So there are these different steps that we have to do, and I will take you through an example of doing that in one moment. There are various properties of a matrix which it's useful to remember. If we find the determinant of an inverse, it's 1 over the determinant of the original matrix. This property here, we'll prove that a bit later, that the inverse of AB is B inverse A inverse. Similar proof here. And that if a matrix is self-inverse, A inverse is equal to A. So let's get on and find some inverse matrices. So the first thing you do when finding an inverse is you find the determinant, because if the determinant is 0, you cannot find an inverse. So for this first one, we can say that det A is equal to 28 minus 24, which is 4. So the determinant is not equal to 0, so we are going to be able to find the inverse of this. So A inverse, if we say this matrix was called A, is going to be 1 over 4. Now we swap the diagonal, so those swap over, and we make these numbers change sign, so minus 8 and minus 3. And that's the inverse. We could check by multiplying this inverse, this matrix by this one, and it should give us the identity matrix. You don't have to bring the 4 inside here, so you could write this as 1 minus 2 minus 3/4 and 7 over 4. You don't need to do that really. It's often easier to leave the number outside here. If we call this matrix B, first thing we do is find det of B, and that's equal to 2 times 4 minus 8 times 1, which is 0. So there is no inverse, and we stop there. That's why you always find the determinant first of all. Right, let's have a look at the 3 by 3, the inverse of a 3 by 3 matrix. Right, the first thing you do is you find the determinant. So step 1 is find the determinant. So looking back to the previous page, that's step 1. So the determinant of this matrix, which I'm going to call A, is equal to, we're going to have 2 multiplied by 4052, the determinant of that, minus 1 times 20 minus 12, plus minus 1 on this minor here, which is going to be 24 minus 1, 5. And you'll see in a moment why I write this out in such a long way for this question. So that's going to be 2 multiplied by 8. Take away 1 multiplied by 4 minus 1 multiplied by 14. And when you work that out, you get minus 2. So the determinant is not equal to 0, so we are going to be able to find the inverse. Step 2 is to find the matrix of minors. So the matrix of minors. Now what we do for this is we replace every element in the matrix with its minor. Now if you remember, the minor is the determinant of the matrix that's left behind when you cross out the row and the column of the element. So this here, this 4052, the det of that, is the minor of that 2 up there. So the minor of that first one is 8. The minor of the top row middle element is going to be 4. And the minor here is going to be 14. Let's find the minor of the element 2 that's in the second row, first column. So we would cross out that row and that column, and we would be left with 1 minus 1, 5, 2. That would be the minor of this 2 here. Let's just double check that. So crossing out that row and that column, 1, 5 minus 1, 2. Good, that's right. And so when I work out the determinant of that, I get 2 take away minus 5, so that's 2 plus 5, and that is 7. So you could just pause the video now and work out the minors of the remaining elements. So if you have paused the video, here are the answers you should have got. So that's the matrix of minors. We now need to find what's called the matrix of cofactors. And the matrix of cofactors is what you get when you apply, it's called the alternating rule of signs, and you apply plus minus signs to this matrix of minors. So what that means is we apply this rule here to each of the elements. So where it says plus, that doesn't mean it's a positive number. It means leave the sign as it is. If it's minus, it means change the sign. So in this matrix here, all the elements are positive. So it's going to end up being 8 minus 4, 14, then minus 7, 3 minus 11, then 4 minus 2, 6. But if, for instance, this had been negative 2, it would have become positive 2 when we switched it. If that had been a negative 6, it would have stayed as a negative 6. So these plus minuses mean leave the sign unchanged, change the sign. So we've now got the matrix of cofactors. What we do now is we find the transpose of that. So we find the transpose of the matrix of cofactors. This is often called C. So we are going to write the rows as the columns. So we're going to go 8 minus 4, 14, minus 7, 3, minus 11, 4, minus 2, 6. So I've taken each row and written it as a column. And I'm almost there. The very last step is to divide by the determinant. So A inverse is going to be 1 over, now the determinant was minus 2. So I'm going to put minus 2 like that. So I want minus a half multiplied by this matrix here. So that's 8 minus 7, 4, minus 4, 3, minus 2, 14, minus 11, 6. And that is the inverse. I could take the minus inside here. I could divide by 2, but you don't actually have to do that. You might be thinking this is long. It is long. Your calculator will do it for you. So you need to know how to do it with your calculator, but you could be asked to do this algebraically. So you need to know the method. So it's important to remember that there are 5 steps. Find the determinant, find the matrix of minors, find the cofactors, which is the alternating signs, find the transpose, and then divide. The final section we're going to look at is what happens when you do something that's really called matrix algebra. If you go on to university, you will cover quite a lot of this work. So suppose we want to find the inverse of PQ. So we've multiplied P and Q together, we want to find the inverse. Let's suppose that C is equal to PQ inverse. So we want to find this value here. So if C is equal to the inverse of PQ, then that means that if we multiply PQ by C, that's going to be the identity, because that's the definition of the inverse. Now what I'm going to do now is I'm going to pre-multiply by P inverse. And it's important to remember that in matrix multiplication, the order matters. So I'm going to write down that I've done that. So I've pre-multiplied by P inverse. So what do I get here? Well, P inverse times P is the identity matrix, and the identity times anything is just that same thing. So I've got now that P inverse is equal to QC. I'm now going to pre-multiply by Q inverse. So I get Q inverse Q multiplied by C is Q inverse P inverse. And carrying on, this gives me C, because this is the identity, is equal to Q inverse P inverse. So I've proved what they wanted you to show, that if you've got a matrix PQ and you want to find the inverse of it, it will be Q inverse P inverse. And you will see some questions where you have to use this kind of matrix algebra, and there's another example here to look at. But that is a small part of this chapter. So if you find this a bit of a new concept to be doing algebra essentially with matrices, then don't worry, you will get used to it, but it's not a large part of this section of the course.